Hello and a very good day to everyone. We are pleased to present our project titled Synchronous Abnormal Counter using JK flip-flop. This project was carried out under the guidance of our lecturer, Encik Radhi Hussein bin Ramli. Our team is made up of 3 dedicated members. First is Nur Fatihah, next is Nurin Hazwani binti Hisham and Akidah Darisha binti Muhammad Nazri. In this project, we built a 7-state synchronous abnormal counter using JK flip-flops. Unlike a regular counter that simply increases step by step, our design follows a special non-sequential pattern. The counter works with 4-bit binary state and each transition was carefully chosen to match the abnormal sequence assigned to us. To bring the design to life, we used multi-sim software for simulation. The result were then displayed on a 7-segment display. Our project was carried out in 8 clear steps. First, we first defined the abnormal sequence, then created the truth table to map present to next states, built the JK excitation table to know the inputs for each flip-flops, then used K-maps to simplify the logic, derived the Boolean equation from those simplifications, designed the circuit diagram based on the equation, verified the design with a simulation video in multisim, and finally drew our conclusion from the result. This slide shows the sequence of state that our abnormal counter follows. Instead of counting in the usual binary order, the counter jumps between specific state, which is 0, 8, 3, B, A, E, and 6. Here we can see the truth table that maps the present state to the next state. Each row represents one transition in the abnormal sequence. The left side shows the present state in a binary form. The right side shows the next state that the counter should move to after a clock pulse. This truth table is essential because it defines the exact behavior of the counter. Without it, we would not know how to design the excitation inputs for the flip-flops. This table introduces the concept of excitation. Excitation means determining what inputs J and K must be to achieve the desired transition from the present state to the next state. The JK flip-flop has 4 possible input conditions. If the present state is 0, then the next state is at 0, J equal to 0, K equal to X, don't care. If the present state is 0, then the next state is 1, J equal to 1, K equal to don't care. If the present state is 1 and the next state is 0, J equal to don't care, K equal to 1. If the present state is 1 and the next state is 1, J equal to don't care and K equal to 0. By applying this rule, we can determine the required J and K inputs for each flip-flop in the counter. This prepares us for the detailed excitation table shown in the next slide. Now let's look at the JK excitation table, which is the key part of our designing abnormal counter. This table shows how each flip-flop should behave to transition from the present state to the next state. We are working with the 4-bit system, so we have 4 flip-flops, JKFF3 until 0, corresponding to bits A3 down to A0. For each row, the left side shows the current binary state of the counter, the middle shows the next state the counter should move to, the right side shows the required J and K's input for each flip-flops to make that transition happens. To determine this input, we use the JK flip-flops behavior rules shown in the smaller table. If the current state is 0, then we want to stay at 0, J equal to 0, K equal to don't care. If we want to go from 0 to 1, J equal to 1, K equal to don't care. If we want to go from 1 to 0, J equal to don't care, K equal to 1. From 1 to 1, J equal to X and K equal to 0. We apply this rule to each bit in every row. For example, in the first row, the counter goes from 81000 to 0000 in binary. A3 goes from 1 to 0, J3 equal to X and K3 equal to 1. A2 goes from 0 to 0, J2 equal to 0, K2 equal to don't care. A1 goes from 0 to 0, J1 equal to 0, K1 equal to don't care. A0 goes from 0 to 0, J0 equal to 0, K0 equal to don't care. We repeat this process for each row in the table. This gives us the exact input condition needed for the JK flip-flops to follow the abnormal counting sequence. This is the final of the output that we got from our JK excitation truth table.
Next, I will explain about the Karnoff map or K-map and how we use it to get the Boolean equation. The K-map is a method used to simplify Boolean expression. It helps us to reduce complex logic equations into simpler forms, which means fewer logic gates are needed when we build the circuit. This makes the circuit more efficient and easy to understand. In K-map, the value from the truth table are placed in a grid using 1, 0, and don't care values. The arrangement of the cells follow gray code so that only one variable changes between the adjacent cells. So this is the K-map for J3, K-map for K3, K-map for J2, K-map for K2, K-map for J1, K-map for K-map for J0, and the last one is the K-map for K0. So the next part will be Boolean equation. So after filling in the K-map, we group the K-map into the size of 1, 2, 4, or 8, and they should be as large as possible. So grouping helps us eliminate unnecessary variables. Once the grouping is done, we identify which variable remain constant in each group. These constant variables are then used to form simplified Boolean expression. Finally, the simplified Boolean equation obtained from the K-map and can be directly used to design the logic circuit. So, this is the Boolean equation for J3, K3, J2, K2, J1, K1, J0, and the last one is J0.
Okay, next is circuit diagram. In this video, I will explain the design and operation of a 7-stage synchronous abnormal counter using JK flip-flop. IC 7473 simulate in multisim. The components used in circuit for IC 7473 is JK flip-flop, VCC, ground, a cloud voltage source, hexadecimal display, which is DCD hex for probe to observe the output signal, and we have 2 gate OR and 3 gate AND. For IC first is J3 and K3, IC second is J2 K2, IC third is J1 K1, IC fourth is J0 K0. Equation for J3 is A1 bar or A0. For K3 is A1 bar or A2. Equation for J2 is A1 bar and A0 bar. For K2 is A3 bar. And then J1 is A3, K1 is A0 bar and A3 bar. And the last one, equation for J0 is A3 and A1 bar. For K0 is A3. When the multisim is run, the output will be start from 0, 8, 3, B, A, E, 6, and will be repeat the circle. Please confirm that the counter operate correctly according to the given specification. In conclusion, the 7-stage synchronous abnormal counter using JK flip-flop IC7473 has been successfully designed and simulated in multi-sim. The situation result match the required output.
In conclusion, this project successfully achieved the design and simulation of a 4-bit synchronous non-sequential counter utilizing JK flip-flops. The system was engineered to follow a specific 7-state abnormal sequence 0, 8, 3, B, A, E, and 6. The circuit was simulated through multisim, where the result confirms simultaneous state transition across all flip-flop stages driven by a common clock signal. The integration of a hexadecimal decoder and a 7-segment display provided real-time visual validation of the sequence. The successful operation of the circuit demonstrates a comprehensive mastery of synchronous state machine design and digital logic implementation.